That's it until after spring break. All right, today's problem that we're gonna look at, obviously we're in vectors. We're gonna be looking at, let me get a color, we can see a little bit better. We're gonna be looking at distance from point to a line. Worst P ever. Distance from a point to a line. And so we're gonna need a point, we're gonna need a line. We're gonna need point A is 1, 2, 3. Vector equation of a line, L. We're gonna do 5, 7, 9, 3, 2, 1. And here's our question. How far is that point from that line? Well, what we've learned, what we've talked about so far is the point on the line? We've done that. And we could try, but it doesn't really sound like it's gonna work because the whole question is asking how far away is it? So that doesn't seem like it's worth our time. How are we gonna find the distance from the point to a line? Well, we could use the distance formula, which is something that we've even used in class a little bit when it comes to like the magnitude of a vector, is basically just the distance formula. The distance formula is, everybody got this written down? Sweet. Ideas, and I guess I'm coming up with all the ideas, so let me help you with the first one. Distance formula. Square root, that's when you have like x minus x squared plus y minus y squared plus, and we're in 3 dimensions, z minus z squared. Distance formula probably going to be pretty good if we're asking about the distance between two things. But the distance between what? Because this distance, let's see, what am I going to write on this by? This distance here needs 2 points, right? We can't do it with the distance in a line.
Can you get the perpendicular vector line?
Exactly, love it, right? The idea is there is a point that is the closest point on line L. And so if we, and I know we're in 3 dimensions and I'm obviously drawing in 2 dimensions, so you'll just have to trust me a little bit here, but if we call this A and we call this L, there are many points on L and they all have different distances. They all have different distances. So a question like this, which says distance from a point to a line, isn't really ever going to be asked because it could be close if you look at the close points, or far away. So it will tell you the shortest distance from a line. Theoretically, there is a point that's an infinite distance away. So it'll always be asking you about the shortest distance. So if we're looking for all of the shortest distances, just like Devin was saying, we're not going to be just randomly picking tiles or points. These ones that are far away are clearly going to be wrong. And as we get closer, it's going to be clear that the closest distance between the point and the line will travel perpendicular to the line. That the shortest distance between A and L will be a perpendicular line. But again, the verbiage is still kind of struggling there. So what we're gonna do is we're gonna say that there's another point, okay? That there is point P. And that way we can pick our point and maybe label it as P. And this will help us with our verbiage, help us talk about what we need to talk about. That the shortest distance between A and line L, if P is on line L, that from A to P, which could be a vector AP, is perpendicular to L. Now this is not a new theory when it comes to lines. The shortest distance between 2 points is a straight line. Obviously we're going to use that. The shortest distance between a line and a point is a perpendicular. That's kind of a geometry thing. Of course we're in 3 dimensions now, but still the same case. Perpendicular. Now, we haven't talked a lot about perpendicular in 3 dimensions. We've talked about collinear, parallel, intersect, and skew, and we have not talked about perpendicular there. But the one thing about perpendicular that's always true with vectors is that perpendicular vectors have a dot product of 0. So we're going to bring that all the way back from like 3 weeks ago and focus on that as our main point. Okay, so our new goal is to find P. Our new objective is to find point P. If we can find point P, we know that from A to P is perpendicular to L, and from there we can figure it out. So, this is our strategy. We gotta find point P. Let's go over to the start of the question now. If we're gonna start this question, we need things that we've come up with that are true, things and formulas that we can start to work in. Obviously we're looking for point P, but that's just the name of something. That's kind of a mystery, okay? Things that we do know is that from A to P is perpendicular with line L. That means that from A to P is perpendicular to line L. Again, that's more or less writing the same thing twice. Maybe you don't need to write that down, but just to make it super clear. And so that means I'm going to kind of leave this perpendicular symbol here, almost like my equal sign. Let's work on the left side first. How can we use, again, it's been a while since I've shown this, but here's our point A and our line L. How can we write this down? From A to P. We still don't know where P is, but we do know that P is on L. So here's what we're thinking. Oh, bored. It's late in the day, 4th period, loses his mind a little bit. Point A is here floating somewhere, and our goal is to find point P, which is on L, which means point P has a lambda value. Point P is 579 plus some lambda, I don't know what it is, times the direction vector of 3, 2, 1. And if we want to find P, we have a new goal, to find the lambda of P. If we find the lambda of P, then we can actually find what we're looking for, which is P. So we don't know lambda yet, which means we can't really figure out P yet. We have to do a little bit of math to find lambda, to find P. So in order to find this, I'm going to start off by listing, I'm going to list point A. Vector form here, the position vector, 1, 2, 3. And I'm going to subtract P from A. That is how you would travel from A to P. You would do P minus A. And so now I'm going to write P. Now P is actually just the whole L because we don't know what lambda needs to be. So here we have 579 plus lambda 321 and this it's not really P because it's just L, but there's some lambda that's gonna turn that L into the P. So far, we have this thing, in your head, it's kind of like P. In reality, it's just the line L. And that is perpendicular to line L. Well, if we're talking about perpendicular, we don't need, I know that this is L and this is L, but when it comes to perpendicularness, we don't need the entire L. We just need the direction vector, because that's the only thing that really matters when it comes to slope. So over here, we're gonna set it up with 3, 2, 1. Okay, now this is where we have to do all of the big stepping. At this point, everything else is just gonna be kind of standard stuff we've done before, but this setup was the big leap. So let me just go through it one more time just to try to clarify a little bit. We know that there is a point P, but we don't know what it is. And that from A to P is gonna be perpendicular to L. That wave is the shortest distance. Well, from A to P being perpendicular to L, if you're gonna travel from A to P, then you would do P minus A. So here's our A. This is just from the question. 1, 2, 3 comes right from the top. P, we don't know what P is. It's L, or lambda, some sort of lambda that's gonna turn the line into the point P. And that's perpendicular to L. And this is only the direction vector from L, because that's all that matters for perpendicularness. Okay, if we've made it this far, we're getting very close to the end of kind of part 1. We need to do some math really quick, because this over here on the left side is kind of a mess, okay? I understand if we have maybe just this as a vector equation, vector plus lambda vector, but vector plus lambda vector minus vector is too many things that we're juggling around, okay? If we're thinking about common and you know, adding and subtracting like terms, this middle direction vector has the lambda, but this vector and this vector are like terms. They're just plain old vectors. They don't have any multiplication on them or any kind of variable or anything. So when it says to do subtraction, we're gonna be subtracting these two, not the direction vector with the lambda, but these two. So when we subtract this, it's very easy to do. 5 minus 1 is 4. 7 minus 2 is 5. 9 minus 3 is 6. Okay, now we can't really I'm running out here. We can't really simplify this much more because we don't have any more like terms. I think it's time that we need to cash in. I think it's time that we need to cash in our understanding of perpendicular vectors have a dot product of 0. And so, I'll just make a little bit of room. Zooming in, perpendicular vectors have a dot product of 0. That means that if we do this in the parametric equations, the x's times the x's plus the y's times the y's plus the z's times the z's is equal to 0. Now over here, it's messy because we've got 4 plus lambda 3 and 5 plus lambda 2 and all of these values, but we're just gonna have to deal with that, and it's gonna be a little bit of distributing. Mathematically, it's not that hard. So we're gonna take the x's and multiply them together. That's 4 plus 3 lambda. And we're gonna multiply that by 3. Now, it's kind of a mess to use the dot to mean multiply when we're already doing dot product. So I'm gonna rewrite that 3 in the front, which is kind of getting their order backwards, but again, that's just because I don't want the grammar to be weird. I'm gonna do the y's, 5 plus 2 lambda, 5 plus 2 lambda, and I'm gonna put the 2 in front just because it looks better. And then the last one here is 6 plus 1 lambda, 6 plus 1 lambda, and I'm gonna distribute a 1. Well, distributing a 1 is a waste of time, so I'm not gonna do anything there. And all of this is equal to 0, and all of this has only one variable, lambda. Algebra 1 time, distribute, combine like terms, blah, 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 finish the question. Distribute 12 plus 9 lambda, distribute 10 plus 4 lambda, distribute, I don't even have to distribute, 6 plus lambda is equal to 0. Really running out of room here, but finishing up, combining like terms, I've got 9 lambdas, 4 lambdas, and 1 lambda. That makes 14 lambdas. I'm gonna subtract all this stuff to the other side. I'm gonna subtract 12, 10, and 6. That's 28, and it's gonna be negative when it goes to the other side of the equal sign. Don't lose your equal sign. Make sure you keep track of where that equal sign's at. Finish with divide by 14, divide by 14, and I'm gonna get that lambda equals -2. All right, now these are long questions, okay? What we've done so far, I'm gonna zoom out a little bit. It's Algebra 1, you can do that without me. Oh, I don't know what the board's up to today. Okay, what we've done so far. The shortest distance from a point to a line. We need perpendicular, which means we need to set it up, and the setup was everything. P minus A, perpendicular to the direction vector, even though P is just the entire line, that way we can actually make some progress to find lambda, to find P kind of backwards. Now that we have lambda, we're not even really close to the answer yet. Lambda is good. Lambda helps us find P. So in order to finish this, well, ironic, in order to end this start section, let's find what P actually is. Using lambda, P is equal to L, which is 579 plus lambda, which is -2, and then 3, 2, 1. I actually do it 5 plus -2 times 3. 5 plus -6 is -1. 7 plus -2 times 2, 7 minus 4 is 3, and 9 plus -2 times 1, 9 minus 2 is 7. Here it is. This is P's position vector. There is point P. It's finally showed up. I've done a couple kind of starting over and reminding you where we're going, so I'm just gonna proceed forward now so that it's not too repetitive. P is good. P is very nice. We definitely want P. P is the shortest, the closest point from A to line L. But we still have not answered the question of what is the distance. So in order to finish this question, it's gonna be shorter than the start, but in order to finish this question, we need to actually find the distance. The distance formula, just to write it again, is x minus x squared, y minus y squared, z minus z squared. All of that is square rooted. Point A is 1, 2, 3. Point P, we just figured it out, negative 1, 3, 7. And P is line L, right? It's the closest point to A on line L. That means we just need to do the distance, which is the subtracting. I'm gonna do A minus P. If you do A minus P or P minus A, it doesn't make a difference because you have all the square terms, so you'll be all right either way. I'll do A minus P, how about that? Square root of parentheses squared plus parentheses squared plus parentheses squared. I'll put my A, 1, 2, 3, minus, 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 and then I'll put my P terms, negative 1, 3, and 7. That's the square root of 1 minus negative 1 is 2. 2 squared is 4. 2 minus 3, negative 1. Negative 1 squared, 1. 3 minus 7, 4. 4 squared, 16. And that means our final answer is the square root 21. And that is the end of this question. We have found the distance between the point and the line.
Most of these questions go back earlier.
Well, we don't, I mean, it could be either one, because why not? We don't really need the calculator, you know, it could be either. We don't really need the calculator. If it's not the calculator, I mean, I did it without the calculator this whole time. If it was a calculator question, you could not have to worry about this algebra. You can just type it all in, get your number. That's a decimal, and the square root 21 is like 4.6 or 4.5 or something, you know, whatever. You get a number like that. With the calculator, I'm not sure really what that advantage is. Normally the calculator questions are gonna require you to use something like the sine, cosine, tangent button that you can't do in your head, or it's gonna require you to, you know, look at the graph and see where two things intersect. Now, where two things intersect on the calculator is only two-dimensional, so I don't really see how that would help. I would say a question like this is most likely to be on a non-calculator exam. At the same time, my first year doing this, so we'll see. Yeah, it's a long question for sure. The hardest part, 100%, is this setup here, okay? AP is perpendicular to L, and the way that we have AP is from A to P, which is P minus A, and for P, we just put the whole L. I know I said that a couple times, but it's easy to get stuck at that step. Once you get there, your kind of momentum can take you most of the rest of the question. All right, that's it for notes for today. Just the one type of question.